you can be absolutely sure that on graded problem set 4 and maybe the final, you're going to see a question of this kind where, I ask you to construct some confidence interval. And the reason that I like this is that, it just reminds you what a confidence interval is, how you construct it. It's a great exercise. And of course, when I ask you to do it for a graded problem set or something, I'm gonna pick some oddball confidence interval, like a 97.5% or a 99.9% confidence interval, or something along those lines, just for you to practice with. But if you know about the inverse t-tail function and the t-tail function, you're not going to make any mistakes, because you should always know that you can use one of those functions to cross-check or double-check the other. Like that's what I'm doing in this circumstance. To get a 90% confidence interval, right, I need to find the t statistics such that there's 5% in the upper tail and 5% in the lower tail. And so this is what I'm doing, right? With this command, with 24 degrees of freedom, 5% in the upper tail, that corresponds to a t statistic of 1.71088. And then I can go ahead and use, just because I'm prone to mistakes, I go ahead and use t-tail function to double check that. Here is number 2 is just a straightforward problem where we have a two-sided hypothesis test, but that two-sided hypothesis test is, about beta 1 equal 1 versus the alternative that it's not equal to 1. This is a, pretty straightforward kind of question. The only thing that's not straightforward in it, of course, is that we end up getting a p-value of 0.055, and this is one of those situations, that's not going to be on a graded problem set, not going to be on a on a final exam, but just to think about the judgment involved. All right. And so again, I'm not evaluating this on you on this, but I want you to point this out. Suppose that in this circumstance, we had pre-specified a significance level of 5%, right? And so then we get a p-value of 0.055, right? So, what do we end up getting out of this? It doesn't quite reach the level of the preset significance level, but it doesn't seem like the null hypothesis should be completely off the hook either, because, 0.055 is pretty darn close to 0.05. And you think about the kind of evidence here, right? We would have been willing to reject the null hypothesis if we got, a test statistic that was so extreme, we would only expect to get it in 50 in 1,000 random samples. We end up getting one that's 55 in 1,000. There we have this kind of ambiguous information that's kind of saying, it wasn't our preset significance level. But on the other hand, it clearly indicates some problems with the null hypothesis. I'm just presenting you with that because that's one of those difficult questions you have to use. You have to encounter sometimes, right? Would I fail to reject the null hypothesis in this circumstance? Well, okay, if you're going to say that, that's fine. All right, so okay, that's enough for you. How about if it was 0.051 or 0.0501? this is really about the evidence against contradicting the assumption that you make in the null. And as you get towards that critical value, there really isn't any different weight of evidence. It's essentially the same. And that's a tough question. And I'm just pointing that out and saying, sometimes you get into that situation where it's not clear cut. It doesn't quite get to this pre-specified significance level. So what do? You have to use your judgment. Is that then, are you going to say, well, that really is enough weight against the null hypothesis that I'm going to not assume that beta 1 is equal to 1. This was question 3 was a straightforward problem involving one-sided significance levels and a one-sided hypothesis test. We clearly had a theory that where the alternative hypothesis implied a value greater than 0. So we applied the one-sided significance level. And one of the ways that you can answer this was using this value, right? Because the Stator p-value for the default two-sided test in this circumstance is not correct, but it's useful because we can divide by 2, right? And so that would be the suggested p-value. I did also want you to go ahead and use the t-tail function in this, just to recognize if you're a little bit more careful and use that t-tail function, it's not a huge difference by any means, but you can be a little bit more precise about the p-value you obtain. And here is a question where we applied the theta method, right? And what I wanted you to do, give these precise interpretations, but then talk about the circumstance where we thought the effect of another year of experience was the same as another year of tenure. And so, it's a test involving 2 parameters. And so we're going to apply the theta method, right? There's the hypothesis. So we're going to let theta equal to beta 2 minus beta 3, and we just solve for one or the other. It doesn't matter which, we'd get the same conclusion. Notice that when we, we do the algebra, and it says, oh, the theta that's going to be the on the parameter on the variable experience, which is 0.003. All right, and and I'm just pointing out to you, if you wanted to think about it this way, you could still reconstruct our parameter estimates from up here, but the big point here is once we get to that estimate of 0.003, we get a p-value of essentially 0.5, right? So you'd expect something that extreme in about half of all random samples. That's no evidence against the null hypothesis that they are equal. And finally, we have this campaign and expenditures and the vote share. Remember that the vote is a percentage, and that we've got vote on the left-hand side, and we've got logs on the left-hand side. That means we've got to interpret these, by dividing by 100. And then so it's a percentage point change in the dependent variable per a 1% increase in expenditure by A or expenditure by B. And then I said, hey, let's think about, in terms of the parameters, state the null hypothesis that effect of a 1% increase in candidate A's expenditures is offset by a 1% increase in candidate B's expenditures. And sometimes I get students who want to say, oh, that must mean beta 1 equal beta 2. And no, that's nothing like that. I mean, it's the opposite of that in a sense, because what we're saying is, if you said beta 1 equal beta 2, that means that if I increase my expenditures by 1%, it's the same effect as if my opponent increased his expenditures by 1%. No, that's not what that doesn't make any sense. You want that they are opposite in direction, but of the same magnitude, but opposite in direction. So that when you add the two up, it is equal to 0. That's offset. And again, this is a theta method problem. We can figure out we can figure out from our original regression what the difference is going to be, and then apply the theta method. And when you just work out the algebra, we end up having theta on the log expenditure B variable. And we can always double check ourselves because there it is there. Here it is calculated from our original model. So we got the right, we did the theta method correctly, but now we have a standard error and 95% confidence interval as well. And, great thing here, we can now definitively say, oh yeah, we can test that null hypothesis. We get a p-value of 0.32. And so either the null hypothesis is false, or we expect to get a t statistic as extreme as 1 or -1 in about nearly 1/3 of nearly 1 in every 3 random samples, or 31 in 100 if you want to be a little bit more precise, or 32 in 100 I guess is the correct value. Are there any questions from this homework problem or practice set problem that you'd like to ask now? You're always free to ask, but do you have any questions now? All right. You will remember that we were talking about, we'd gone through a procedure, and we had set up the F-test, right? We tested this hypothesis concerning the effect of another year of education at a community college versus a 4-year college. We've done that using the t-test, the theta method, and now we then did it using the F-test, because the F-test is more general, although, as we've talked about, it's a little tricky it's a lot tricky in terms of doing one-sided hypothesis tests, so we just do two-sided with the F statistic. And we figured out, oh, okay, yeah, we could do this. We could run this all by hand, do the F statistic by hand, which means actually running the restricted model, getting the sum of squared residuals, constructing the F statistic, et cetera. Or, if we understand that, it's not magic to us, then we can just use the shorthand, the test statistic, the shortcut. And essentially the idea there, it's very kind of simple in that you can understand the syntax, but it's just by kind of thinking about it and saying, if I was going to display the parameter estimate for the return to a year at the community college, that's how I'd type it. Well, in using test, we can use exactly that same notation, and we get, the F statistic and the p-value. Now, if you recall, I said that we would start out with a in-class question, and that in-class question had to do with, oops, let me see here, screen new share, is the test statistic that we obtained the same or different? Man, what am I doing here? You're just seeing me?
Yeah, we just see the notes page.
iPhone via cable. Yeah, there it is. All right, I'm having You can do this a zillion times and then all of a sudden it doesn't quite work. All right, there, maybe that's it. All right, all right. Hmm. Um, all right, for reasons I cannot understand, I'm having trouble getting my my iPad to show up where I usually show the in-class questions. So I'm just gonna try to, I can't go to that screen, but you can see here clearly that we have the F statistic, we have the p-value, et cetera. And the question is simply, we already tested this hypothesis test that beta 1 is equal to beta 2 using a t-test. Is the f-test equivalent or different? That is the question. And Chen Preet, it is your turn to answer an in-class question.
Yes, Professor.
Yes, so is the f-test that we just did, these results we're showing, is that equivalent or different to the test statistic that we, and the result that we obtained when we applied the theta method and used a t-statistic?
I think it's equivalent
And why do you say it's equivalent?
because we have the same p-value for that.
Yeah, there you go, there you go. It's so, yeah, I mean, people, like, sometimes have people struggle with this question. Hey, if these two things didn't give us, if they weren't equivalent in this circumstance, then we'd be in big trouble. Like that would be a problem. We'd like get different things from different tests. So if you go back up here where I presented the theta method, notice that when I take the t-statistic and square it, right, we have the same p-value, but not only that, when I take the t-statistic, oh, I'm not showing you. Okay, sorry. All right, let's do that. At least we can get that. When I take the t-statistic and I square that, I get the f statistic. So that's true anytime we have a single linear restriction, right? A single linear restriction, we could test using a t-test, we could test using an f-test. They're equivalent. And one of the ways that you can think of that equivalence is you square the t-statistic and you get the f-test, f statistic. Okay, here is one more example on you know, figuring out or you know, using the f statistic. And this is an interesting one. So if you're an assessor, right? If you're in the you know, the governmental assessment office in a county or a city, your job is to try to, as closely as you possibly can, have tax assessments that are as close or that as close as possible reflect the market values of houses, because people have to pay a property tax based upon their assessed value, their property tax based upon a certain percentage of their property value. And so, to be fair, that's what the law says, is that everybody has to pay the same property tax rate. It's a flat tax based upon the value of the property. And so we have in this model a test of the efficiency of assessments. And it's kind of like when I explained the test for market efficiency up here, and I said, well, market efficiency, the expected value of the return, next period, conditional on today's information, is equal to the expected value of the return next period, because if markets are efficient, they incorporate all of today's information. The same idea holds here, in the sense that this idea says, well, once you condition on the assessment, then, once we condition on the log of assessment, then these other regressors tell us nothing about log of price, which is to say, again, conditioning on assessment, log lot size, log square feet, bedrooms, they have no additional predictive power, because all of their predictive power, all the meaning that they have for housing prices, are already incorporated in the assessed values. So that's kind of an interesting, it's an interesting application of hypothesis testing to test this idea of efficiency in a particular situation. So let's see what we can do with this. Here, you can kind of see how this is going to work. It's going to follow the same procedure. If we have the efficiency null, that would mean beta 2, beta 3, and beta 4 are all equal to 0, right? Versus the alternative that HO is not true. At least one of them is non-zero. So we estimate, once you incorporate that set of restrictions, then you just have this very simple model with the regressor log assessment. You estimate the restricted model. We store the sum of squared residuals for a subsequent calculation. We estimate the unrestricted model, right? And we can access the degrees of freedom in the residual and the residual sum of squares. Here's our F statistic, right? The difference in sum of squared residuals divided by 3, because that's the number of restrictions, right? You got 3 equal signs here. That's the number of restrictions. That goes as the numerator degrees of freedom in your F statistic. And then the sum squared residuals for the unrestricted model divided by the degrees of freedom for the unrestricted model. And it turns out we get a p-value, an F statistic, of minor size, and a p-value of 0.46. So again, there, under the assumption that all those parameters, those 3 parameters are equal to 0, what can we say? Hey, either the null hypothesis is false, or we just got one of the 46 in 100 random samples where we get a F statistic this extreme. Again, responding, thinking about the question that Jess asked last time, this is not proving that the null hypothesis is true. We assume the null hypothesis is true, so we can't assume it's true and then say, well, we just proved it's true. No, all we can do in a null hypothesis is say, hey, did we get contradictory information? Sometimes we say, yeah, we did. Sometimes we say, no, this isn't contradictory information at all. And that's what's going on with the p-value. Clearly, going on with the p-value of 0.45. And then we have this example as, you know, once we got to that point, we could look at this and we could say, well, you know, if I understand how to do this by hand, you know, I'll have you do some by hand in practice problem sets, graded problem sets. But if you understand that, if I don't say do it by hand, you're free to do the shortcut. And notice the syntax required here. You need a set of parentheses for each separate restriction. All right, so one equal sign, one restriction, each different restriction has to go in a set of parentheses. And then it's pretty easy then to use the test command, and obviously we're going to get the same F statistic and p-value. All right, so that's kind of where we are. I think this is you know, especially the theta method is a super interesting and useful thing to know about, and it also gives you this great insight into realizing that the model is something that you can take and make your own to specialize it to the special circumstances of the research question you want to ask. I've got more to say. I want to jump as quickly as possible to chapter 5, but if I have any questions on this set of notes before we get there, I'd be happy to answer them.
So
okay.
I
go ahead.
That the T statistic is the ratio of the change or the standard error. That one I can kind of conceptualize. But how would you put into words? I know you said it was like the change in squared residuals per restriction over, what was it?
Yeah.
Residuals per error.
Yep.
And it's just not intuitive understanding what that whole sentence means.
Yeah, I know. What do you want me to do about it? Right. So no, I mean, you know, one of the reasons I started you here, right? When I tried to I said, oh, here's our motivating example. Let's go back and look at this. Here's the unrestricted model, right? And here's the model where we restricted theta equal to 0 and restricted the effect of years at a community college and years at a four-year college to be identical. And I said, well, how would we kind of assess here how you know, to kind of think about, well, is when we make that restriction, is the data crying out and saying, no, you know, we can't possibly do this. You're making us, constraining us ways that just isn't right. Or does the data just say, oh, hum, right? And, you know, so the kind of the way we thought about doing that was to say, oh, well, we could think about it in terms of R squared, right? What's the change in R squared? And that's a really small change in R squared, right? We could think about it in terms of the residual, and that's a really small change in the residual, but it can't just be, we have to get that into relative terms. So we can express the F statistic in terms of the change in SSR, the change in sum of squared residuals, or we could express it in this way, and I don't think I went through this carefully, but the point here is that, yeah, we could actually also write the R squared, the F statistic in terms of the R squared. And I go through the little algebra, you know, relating, because R squared is defined based upon sum of squares total, sum of squared residuals, sum of squares explained, etc. So you can also define that F statistic as the difference in R squared divided by the number of restrictions over 1 minus R squared U divided by the number of parameters in the unrestricted model.
And it's the bottom term, the 1 minus R squared U over number of restrictions or number of parameters in the unrestricted model.
Yeah.
That is a little hinky. What does that represent?
All right. Oh, okay. All right. So like here, let's just think about it this way, and so I don't have to mangle the wording. Remember that we're just going to call this an average. We're going to know when I'm talking about this that it's an average adjusted for the degrees of freedom, but I'm just going to talk about it as an average. So what this does is it says, okay, what's the proportion of the total variation in Y that's not explained by the regressors? That's 1 minus R squared. And then it's going to look at that and say, okay, what's the average per observation?
Okay, yeah, my issue was that I totally forgot that n minus number of parameter or degrees of freedom was just taking essentially the average.
Okay.
That makes a lot more sense.
All right. And you're basically doing the same thing here. It's just it's SSR divided by change in SSR divided by average SSR. Any other questions about this set of notes? Okay, let's talk about chapter 5, which I feel must be, there it is. All right, so here's the big question. You can kind of think about this course. You can think about it as, like you think, oh my gosh, it's like we spent an eternity in chapter 2. I think it's worth spending an eternity in chapter 2 because I think you'll notice as we go on, chapter 2 is where we explain everything, and all, a lot of the things that we look back to, we explain in terms of the concepts from chapter 2. And then, chapter 3, we spent a long time in. Chapter 4, we spent a long time in. Chapter 5, short, sweet, brief. And what we do in chapter 5 is just answer the question, what do we do if the error term is not normally distributed? So what chapter 4 said, and this page gives you the big layout of all the assumptions and then the theorems that we rely on when we apply this tool. And I can't help but emphasize how important that idea is. If you're getting apply these tools, you've got to know the basis for which you rely on them. Why do you rely on them? Well, because under this set of assumptions, OLS provides unbiased estimates of the population parameters, right? Which immediately then tells you, I got to know about the assumptions. So, we got to remember what these assumptions are, what those main results are, and I'm just providing those on a one-page summary here. And in chapter 4, we got around to adding normality, which allowed us to do normality of the error term, which allowed us to do small sample inference. Now, at this point, what we're worried about, or what we want to address is, well, what if the error term is not normally distributed? Can we do inference, right? If the error term is not normally distributed? And the answer is, yeah, of course we can do inference if under that circumstance. Of course we can. And the way that we can do that is to simply have a sample size that is sufficiently large, right? And how large that is, it kind of depends upon how large the departure from normality is. Like if you've got a very minor departure from normality, 30 observations or 30 degrees, let's say 30 degrees of freedom, that ought to be large enough. If the departure from normality is more severe, however, well, then that's kind of a different situation. That's a different story. And, I think we'd have to look at that and say, yeah, we need a greater sample size the higher or larger the divergence from normality. Bottom line is that, if you have a sample size of 500, 400, 300, nobody's going to give you one bit of trouble about, saying I've got a large enough sample to draw on these results. At 100 or 150, then you're kind of jointly saying, well, that's probably well, let's put it this way. I'm saying the departure from normality is not so severe that I can still apply this procedure. And so, if your sample size numbers in the 100s, you can clearly say, yeah, I can draw on these results. If it numbers in the 10s, that's a problem, unless your departure from normality is very small. All right. So what Theorem 5.2 does is say, just forget about MLR6 and have a large sample. And so we have these terms here, and we're going to have to unpack these terms, but it says beta hat J is asymptotically normally distributed. So remember, under the chapter 6 assumptions, we just said it's normally distributed. This says it's normally distributed as the sample size gets large enough. Sigma hat squared is a consistent estimator of the variance of the error term. We're going to talk about what that means in a second, what it means to have a consistent estimator. And for each slope coefficient J, the beta hat J minus beta J divided by the standard error beta hat J is asymptotically standard normal. That is expected value 0 and variance equal to 1. And just, make sure you see, oh, that's different than what we did here, because here we said, oh yeah, beta hat J minus beta J divided by the standard error beta hat J is T distributed. And of course that has a expected value of 0 as well, but it had a T distribution has more area in the tails. So there's these statements here. Essentially, what we're going to say is that's what allows us to do this, to do the inference that we've learned, confidence interval, hypothesis testing, theta method, all these things, as long as our sample size is large enough without having to invoke normality of the error term. So let's go through these. So one thing this does is it makes reference to a normal distribution rather than a T distribution. And so, I guess I'll first say asymptotically normally distributed. What that means is as long as the sample size is large enough. Technically, it means, oh, you're going to let the sample size go to infinity, but that's not we're not doing that in a practical sense. We're just talking about that in math sense to make these asymptotic arguments. And our judgment is going to say, yeah, a couple hundred observations, we're good. Okay, so yeah, here it says, this makes reference to the normal distribution. The previous made reference to the T, but we want to know T goes to Z as the sample size gets large. In the previous example, from the previous set of notes, we had a sample size of what? 7,000. With our community college versus four-year college example, even though we had a sample size of 7,000, Stata continued to show us T statistics. But what we want to know is there's no difference between a T statistic and a Z statistic after you get to 120 degrees of freedom. So, and this graph shows you, yeah, there's a big difference between the standard normal density, which is the really thin lines here, and the T density when the degrees of freedom are equal to 5. And you can still kind of see it when the degrees of freedom are equal to 30. But if I graph for you, degrees of freedom equal to 100, 60 or 100 here, it'd be so much harder to be able to, tell exactly how those distributions differ from the normal distribution, right? So that's one part of it. This makes reference to the consistency of an estimator. And I'm going to take a few minutes to talk about consistency. Consistency is an interesting concept. And I try to explain it here saying consistency allows you to say, hey, I can get it wrong in the sense of having a biased estimator when the sample size is small, but when n gets large, we let n go to infinity, I have my estimator converges to the population parameter. And I think the easiest way to understand this is through examples to kind of recognize what it means to have an estimator that's biased but consistent, right? Up to this point, we've only talked about unbiased estimators. Now we're going to say, well, we can have an estimator that's biased but consistent. All right, so for example, we're going to, we want to estimate expected value. We're going to use that. We're going to use y bar because it's an unbiased estimator. We said variance of y bar is sigma squared y divided by n. And we said s squared is an unbiased estimator of the variance of y, right? So the expected value of s squared is equal to sigma squared y. And that's important because that's where we get this, that's where we get the standard error of y bar. The standard error of y bar, we're going to take that s squared, to substitute for sigma squared y, divide by n, take the square root, and that's our standard error of y bar, and that's how we construct confidence intervals and so on. Now, I just want you to think about a different estimator. Call it W, instead of s squared, call it w squared. And notice the only difference between these two is that instead of dividing by n minus 1 like we do with s squared, I just divide by n, right? And I think you can see there that we're going to realize, well, that's a biased estimator. And it is biased in the sense that obviously that's going to give the estimates for the variance of y would be too small, right? Because we're dividing by n instead of n minus 1. But suppose that our n is 100,000 or 10,000 or 5,000 or 2,000 or 1,000, or even 500. The difference that we obtain because we're dividing by 499 versus 500 are very, very, very small. And so that's an example of something that is a biased but consistent estimator. And I'm going to give you some other examples. Like here's kind of a weird idea. It's one of those things in statistics that's a little bit puzzling, but if you think about it, it's you can see how why that should work. So s squared is an unbiased estimator of the variance of y. But, right, if we thought about instead of using sample variance, we instead used the square root of that, which is the sample standard deviation. It turns out that that's a biased estimator of the standard deviation of y. Sample standard deviation is a biased estimator of the standard deviation of y. But it is nevertheless a consistent estimator of the standard deviation of y. You let the sample size get large enough, it's not going to matter. And again, there's something that, you know, that's a little bit, it seems a little bit weird, but, you know, this, when we take the square root, right, this is a nonlinear function. We got one result in terms of s squared. It's not going to hold when we take the square root. We're no longer going to have an unbiased estimator, but we still have a consistent estimator. Same thing holds. We know that we've talked, and on the previous page, our estimator for the variance of the error term is we take the sum of squared residuals and divide by n minus the number of parameters estimated. You know what? If we divide by n instead, that would be a biased estimator. But I think you can see if we had an n of 500 or 1,000 or 10,000, right? It's not going to make a difference. So that w squared here would be where we divide by n is a biased estimator, but it's a consistent estimator. It gets it right as the sample size gets sufficiently large. If you take the square root of our estimate of the variance of the error term, you get the root mean square error, which is reported in every regression. And it's kind of interesting here with respect to the root mean square error is, once again, even though this is an unbiased estimator of the variance of u, the root mean square error is a biased but consistent estimator of the standard deviation of the standard deviation of the error term, right? So it's just something to kind of think about and realize, okay, you have these, we have things under our very noses that have been close by, like root mean square error or sample standard deviation, that actually they don't satisfy unbiasedness, they satisfy consistency. Along those lines, here's an interesting point, and that is that when you go on from, if you choose to go on from Econ 501, like in the economics program, where you go from Econ 501 to Econ 612, where we study mainly the second half of the Wooldridge textbook plus some additional enriching ideas, right? And then maybe you, and even in that course, you find some situations where we don't have an unbiased estimator. And like when we're using an instrumental variable estimator, like in to overcome the problem of violation of the zero conditional mean assumption, we're going to find that we don't have an unbiased estimator, we only have a consistent estimator. The same thing is true with respect to like Logit, Probit, those kinds of estimators. You know, I don't know if you've heard of these things. Logit, Probit, they're 0-1 estimators, or excuse me, 0-1 values of the dependent variable. And so that's a case of a limited dependent variable. You also have circumstances where you have a censored response, like, well, one kind of censored response is survival time. You know, how long does the light bulb live? How long do people live, you know, that are exposed to something? If you want to estimate how long they're going to live, you've got this censoring problem, because you don't wait until everybody dies to figure this out. You estimate it where some people have died and some people have not. There's a whole range of things where we have limited dependent variables. There's some in a sense, the the dependent variables are limited, 0, 1, or they're a count with lots of zeros. They're not a continuous measure, or they're limited in the sense of these censoring issues, or it's an ordered response instead of all we can say is, oh, this is better than that, is better than that, but we don't know how much better. It's just like satisfactory versus unsatisfactory versus very unsatisfactory. There's also a nonlinear model for that. That's a limited dependent variable. There's a nonlinear model. My point in saying this is to simply say, and there's various examples in chapter 17 of Wooldridge. The unifying theme here is limited dependent variable, and the point of all this is, in all those circumstances, there is no unbiased estimator, there is only a consistent estimator, right? So this idea of consistency is something that's worth knowing about and understanding, and because if you go on and study these specialized models for these specialized circumstances, you're going to run into those things. Peter, you had a question.
Just to rewind real quick, I didn't follow, why is expected value of root s squared not unbiased estimator of sigma y? And I know you said it, but I didn't follow along.
Okay. Yeah. All right. Well, so you want to talk about, I mean, I've got it better laid out, and it's the same logic as I'm trying to explain right here, right? With respect to the sample standard deviation. We've shown, or well, no, actually that's not quite true. We didn't show, we relied on Wooldridge, but we know S squared is an unbiased estimator of the variance of y. Good enough. The sample standard deviation is obtained from taking the square root of S squared. That's our sample standard deviation. This is sample variance. This is sample standard deviation. And what I'm trying to do is just say the expected value of the sample standard deviation is not equal to the standard deviation of y. That is, which is equal to the square root of the population variance. So population standard deviation, population variance, that square root relationship works, but not in terms of the estimator. And, I mean, the only thing I could kind of tell you is, you take this math and you throw in a square root sign, you can see that the math is going to get a lot more complicated, and it's going to be of a nonlinear variety because of the nonlinearity of the square root. Does that help, Peter?
No. I mean, I see that the math will be nonlinear, but also the result would be affected by that same square root. I'm guessing this is something I'll just need to read in the textbook about.
Yeah, you could read it in a textbook or I'm not absolutely sure it would be, you'd see it in this textbook. That's kind of an advanced idea, but you could find stuff on it, but it's just one of those facts of life. Let's see, I'm trying to understand. I don't understand, I don't understand biology all that well, but I understand certain facts of life which, affect me. And so it's kind of like what I'm suggesting we should do here as well. Just warning you against these things. All right, so we've introduced some new theoretical results. And what are we going to do after we have these new theoretical results? Well, we're going to do a Monte Carlo simulation, of course. What else? That's what we always do. So I am, going to kind of try to set up that Monte Carlo simulation for you. And then what's going to happen. You're going to have to tell me what the theoretical predictions are in that table that you can see in the course notes. Now, so the key kind of thing to understand here is that, when you're, the key point that you want to keep in mind is that obviously what we just introduced here in chapter 5 is large sample inference. So it makes a difference how large your sample is. And so to illustrate that, I'm going to show you 4 sample sizes, right? And ranging from 12 to 1,002. And I think you can all see, yeah, there's a big difference in size across those sample sizes. And for a error term here, I am going to use a draw from a particular error distribution based upon a chi-square with 1 degree of freedom, right? So, in a different statistical class, you would have learned about certain kinds of things that under a null hypothesis should follow a chi-square distribution. Like, in a chi-square tables, observed minus expected squared follows a chi-square distribution. Well, that chi-square is this theoretical distribution. It's based upon squaring the z, but it depends upon the degrees of freedom too. And so I'm going to take this chi-square distribution with 1 degree of freedom, and then I'm going to have to adjust that because by definition chi-squares are only have positive values. So I have to, but its expected value is equal to 1, equal to the number of degrees of freedom. So I subtract 1 so that the expected value of u is equal to 0. And we also know in this circumstance that the variance of the error term is equal to 2. All right. So it's a kind of a modest, the variance is not huge here, right? It's equal to 2. And, in other circumstances we've had, depending on the example, I've had like variance equal to 25 or in some other, I think in graded problem set 3, I had variance equal to 225, right? So our variance is relatively small, but do notice that as I show you here, I show you an example of something that one set of 1,002 draws from this chi-square distribution subtracting 1 so that the expected value is equal to 0. And I just want you to see, yeah, that's definitely not normal. In fact, I drew, you can see overlaid that what a normal distribution would look like with the same 0 expected value and the same variance. So it looks way non-normal, way asymmetric. And so, we're going to test our theorem here from chapter 5 based upon its performance with this error distribution across these different sample sizes. Once again, here's our model, 1 plus 3 times x. So we've set the population parameters, beta 1 equal to 3, beta 0 equal to 1. I happen to be drawing these from a uniform distribution, and that gives me a certain prediction, very accurate prediction for what I expect the sum of squares total will be. The fact that I chose a uniform distribution, I could choose something else. I mean, I don't have to choose a uniform distribution. It could be some other distribution, but if you don't like that, you go run your own darned Monte Carlo simulation. This is what I chose, and you want to make different choices, you could, but it wouldn't affect at least this choice. It doesn't affect the theoretical predictions, because no theoretical prediction that we make says anything about the distribution of x, so long as x is not correlated with the error term. So you can see here, I've got these different expected values for the sum of squares total, depending upon the sample size. As before, we're going to do the simulation 10,000 times. And for each of the sample sizes, we're going to do this 10,000 times, regress y and x, and record the results, right? After we've added in that error term from that distribution that's highly non-normal. All right. And you guys already know that what we're doing in our simulation is approximating the sampling distribution of the OLS estimators. So I hope I've worked out my problem with my iPad. What we need to do, so this is an actual experiment, is we need to go over and we need to look at my Stata, so you can shout out some, so you can set the seed. Actually, you're going to set the seed. 54159. That's all Peter. Anybody else want to add to that? No, Peter's got it. All right. So here I'm going to do my program. Let me see. I'm going to make sure I'm in the right directory. I better do that, so I know where to look for these things. And I'm going to, there's my program. I'm going to get it running, run through that. Yep, that'll be good. And so that's going to be running in the background while we're doing the predictions. Now, I'm going to ask this question with respect to the predictions based upon different chapters. All right. So I'm going to ask you to do this in a specific order, not any old order, but in a very specific order. And so the first person needs to tell me what you can say based upon the information we had from chapters 2 and 3. Samaher, what can we say based upon what we know from chapters 2 and 3?
For the mean and the sample variance?
And yeah, or whatever. Well, I don't, you tell me, because that's the question. What can we say? All right, so for mean of beta hat 1, can you make a prediction, and what is it?
Yeah. Would that be the expected value of beta hat 1?
Yeah, and what is that? It's in your notes on the, it's set up there. I mean, you had the answer, so I'll help you, but you gotta look at the notes to be able to get this. But yeah, it's equal to 3.
Okay.
And it's equal to 3 in each of the sample sizes. So it's in the notes, and what we're using here, drawing on, is the expected value of beta hat 1 is equal to the population parameter under assumptions 1 through MLR 1 through 4. All right. What else can you say from chapter 2 with respect to these predictions? From not chapter 2, but chapters 2 through 4. What else can you, not 2 through 4, 2 and 3 for predictions in our Monte Carlo simulation?
So for the sample variance would be the variance over n.
Whoa, where did you get that?
Okay, I'm going over my notes.
Yeah. What? And I'll also I gave you
Oh,
all
sorry. Yes, it's the variance over SST.
Yeah, okay. So it's and the variance is 2 and the SST varies. It's 33. It's 2 divided by 93, 2 divided by 303, and then 2 divided by 3003. And I think you should be able to make one more prediction based upon chapters 2 and 3. And what is that?
So the mean of the variance of the error term.
Yeah. And what's that numerical value?
Okay, that would be.
We set it up. It's 2. I'll give you that. All right. So I did the arithmetic and things in here, so you can see the numerical values, and you can see I've got it nice and neat here. Again, you can see the numerical values of variance there and how it changes. And that is all that we can say based upon the results from chapters 2 and 3. So the next question is, what are the theoretical results or theoretical predictions we can make for any of the remaining cells based upon the results from chapter 4? All right. Priyanka, are you here? Yeah, Priyanka, yes. You're here, right?
Yes, Professor. So I think all those values that we have filled until now will remain same, and number sample 95% will be 500 for all.
Well, I'm going to say here, Priyanka, you got. I don't ask trick questions, but I do ask subtle questions. And, I think what I've got here is a subtle question, because I want to emphasize to you theoretical predictions based upon chapter 4. Everybody think about that for a minute. Priyanka, what did we assume in chapter 4?
To be honest, I really don't remember the concepts by chapter, so I'm really not sure.
Okay, well, if you look, I'm not going to switch from it in my notes, but you look at the first page of, everybody look at the first page of this set of notes that you should have in front of you, either electronically or on paper, and you're going to see, yeah, that you have all that stuff laid out by chapter. And I want you to make sure that you look at that and say, what are the assumptions in chapter 4? And I have to go charge up my computer or else class will be over prematurely. I'll be right back.
That's fine.
Chapter 4.
All right, I'm plugging in. Priyanka, have you got something for us on What are the predictions of chapter 4? What was the central assumption that we added in chapter 4?
MLR5?
No. MLR5 was back in chapter, well, we did a version of it in chapter 2 and chapter 3. But what are we doing? In chapter 4, we added the assumption of normality.
Yeah, normal distribution.
A normal distribution. Do we have a normal distribution in this circumstance? No, we
don't have.
Yeah, we don't have a normal distribution. We have something far from normal.
Right.
And so the answer to this question, and it is a tricky question, is that chapter 4 tells us nothing. We don't have any.
Yeah.
We don't have any theoretical predictions from chapter 4 that tell us what should hold here, because chapter 4 started with the assumption of normality. We can't say that holds here, and so we've got to adjust, right? And we've got nothing from chapter 4, so then we go to chapter 5. And I'm going to go ahead and just cut to the chase here and sort of say, what do we get from chapter 5? Here's basically what we get, right? Number of samples that the 95% confidence interval excludes 3. Well, I'm not going to say it makes a prediction, right? That this makes a prediction when I've got a sample size of 12 or 32, because that's not large. When I get to 102, yeah, okay, there, at least I'm going to be closer to 500. 1,002, yeah, I'm definitely going to think, yeah, 1,002, that's going to be good. I'm going to still expect the mean t statistic to be 0 because of unbiasedness. And then the sample variance of the t statistic, that's actually, remember that the t statistic, again, here it's the beta hat j minus 2 is how we're calculating the population parameter, is how we're calculating that. We don't have any prediction for these very small sample sizes, but when we get to sample variances, sample sizes that are large, well, we think we're going to get values that are very close to 1. So let's real quick, we have enough time, just barely enough time. I'm going to show you my Stator Results screen. So I think you can see, yeah, you can see my Stator Results screen. So, first thing, here's our means and our variances of the beta hat 1, and those correspond, if you look back, those correspond very, very closely to what our theoretical predictions were. Here we had a theoretical prediction of 2, we got a little above, a little below. Here's our 95% confidence interval. I did the 95 and the 99. Like here, with 12, it's not like it's ridiculously off, but that looks more like a 96% confidence interval, not a 95% confidence interval. We're closer and closer, and we're especially, we're much closer to the mark when we get to 1,002. So we're much closer to 0.05 when we get to 1,002. We're quite a bit off at these lower levels, right? And then if we look at the t statistic, notice that the variance of that t statistic is large, and it's getting close to 1 as the sample size increases. All right. Well, that's chapter 5 in a day, because that tells us all the most of the important stuff we want to know. Ooh, let's see. Share. No share. We want to go to, there it is. All right. The only other thing that I would want to emphasize is, this picture shows you that when n is equal to 12, yeah, there's a difference. There's some violations compared to the normal distribution when we compare a normal distribution to the histogram. But we're much, much closer when we get to 1,002. With respect to the t statistic, you can see that when n is equal to 12, the histogram doesn't match it. It's not like it's terrible. It's not like it's egregiously wrong, but it's definitely wrong. All right, and that's chapter 5. A short, sweet trip to chapter 5. With that, we'll quit for the day, and I will see you on Tuesday, where we'll begin talking about topics from chapter 6.